Welcome to the next lectures about liquid chromatography. In a few upcoming videos, we are going to dig into liquid chromatography in particular and look a few different types of it, as well as have a look on the instrumentation of liquid chromatography. So first of all, liquid chromatography has multiple subtypes. There broadly are two types based on different interactions. So there are partitioning-based separations, and there is ion chromatography, which is based then on ion-ion interaction or ion exchange. Partitioning-based separations are by far the most common ones, especially reverse-phase chromatography. Historically, the oldest is normal phase chromatography, and very rapidly developing currently and kind of substituting normal phase chromatography is helic chromatography. But there are also many other types of liquid chromatography. For example, size exclusion chromatography falls under liquid chromatography, as well as, for example, ion pair chromatography, which is kind of a combination of a reverse phase chromatography and ion chromatography. So there are many different types. We could say that roughly about 90, if not more % of the analytical chromatographies are actually reverse phase chromatography. And in this video, we are going to now look more into the instrumentation that is used in liquid chromatography. And this is a fairly generic, though there are some small differences from one chromatography type to another, especially in the detection side. And we will have a look at this one and this as well. A very generic scheme of liquid chromatography instrumentation looks something like this. And if you go to a lab and see a liquid chromatograph, then it's all usually today actually looks like this, a tower of different blocks of instruments. The starting point of this instrumentation is the mobile phase. So these are the mobile phases that are used to carry our sample through the column in liquid chromatography. And in liquid chromatography, we call usually mobile phase also eluent. Eluent is a term that is not used in gas chromatography, but it is used widely in liquid chromatography for the mobile phase. The mobile phase is thereafter degassed in usually an online degasser. So this means that dissolved air, oxygen, nitrogen, other gases potentially that are in the mobile phase are removed. And this is very important to avoid any formation of bubbles in the column when the mobile phase is passing through the column, or also before or after the column, which could be very much disturbing both for the functioning of the instrument as well as to get a nice and reproducible chromatograms. And then after this come pump or pumps. There can be, usually there is one or two pumps, and two pumps are used to mix the two mobile phases. So we can mix two mobile phases online inside in this apparatus. Or if we have one pump, then we can use a mixer actually before the pumps to mix from 2 to 4 different mobile phases. Depending on if we have one pump or we have two pumps, we use either mixing then before the pump. So if we have one pump, then we have to mix before. Or if we have two pumps, then we usually mix the mobile phase after the pumps. And pumps are the source of the pressure that is pushing the mobile phase through the column. So before the pumps, we have low pressure region, but after the pumps, we have already a high pressure region. Pumps direct this solvent to the injection system. So in here, we inject the sample into the flow of the mobile phase. And this is usually done by a loop. So there is a loop which with what we can inject sample sizes from 1 microliter to 100 microliters. Usual sizes are somewhere between 5 and 20 microliters. But also slightly smaller injections can be made, or higher or larger injections of the sample, depending on the sample and its concentration. And then this is further directed to the column. The samples are usually injected in the automatic manner today. This means that we have an auto sampler which comparts something like 50 to 200 samples, which can be then automatically injected and run with the HPLC instrumentation. Then when the sample is directed to the column where the separation starts, the columns are usually thermostated today. So they are sitting in kind of a specialized block of instrument themselves, where the temperature of the column can be regulated. And for this, the incoming eluent together with the sample is already heated, and also the column is heated in this specific compartment. The column temperatures can be somewhat below room temperature to elevated temperatures such as 70 degrees or sometimes even more. There are also high temperature chromatographies present where even temperatures close to 100 or over 100 degrees can be used. But these are very specialized apparatus, because there even water starts boiling, so it needs to be very, very tight. But it is very interesting, and it has been developed over the last maybe 10 years significantly further. But normal HPLC apparatus, yes, has temperatures from something somewhat below a room temperature, like maybe 10 degrees, down to up to then 70 degrees. The limitations in these temperatures are that our sample needs to be stable in the temperature that we are using. So therefore, very many samples actually do not allow us to go very high in the temperature. So we can't maybe even go above 70 degrees, or sometimes even actually we can stay just, mostly we actually stay just at 25 or 30 degrees. However, because the C term in the Van Deemter curve, so the resistance to mass transfer, is becoming less and less limiting when we increase the temperature. This means that we can increase the temperature, and with this get more efficient separation, so get lower theoretical plate numbers, lower theoretical plate heights, higher theoretical plate numbers. So from this point of view, it's preferential, but we need to keep in mind what is the stability of our samples. And lastly, after the sample has been separated here in the column, the sample is directed to a detector. Here in this detector, we have a UV visible spectrometer, which is a light source, a monochromator, and then the monochromatic light is directed through a narrow cell where the effluent from the column is flowing through. And after that, we can register the chromatogram from the signal of the detector. What can also be done, and what is very often done, if we use ultraviolet visible spectroscopy detection in liquid chromatography, then we often use also array detectors here. So this means that we register the full spectrum at once. which is extremely beneficial if we want to detect multiple compounds, or we want to just even maybe characterize our compounds based on where they absorb, or get the additional confirmation by having the full signal of the compounds available. Now, this was a schematic scheme, but how does it look when you go into the lab? So the instrumentation can be, is of course slightly different depending on which vendor's instrument you encounter, but they generally look actually fairly similar to this previous scheme. Everywhere you have mobile phases, which are usually on top of the instrument so that they would be flowing very nicely. You have a pump. Here in this setup, the pump is actually beneath the autosampler, but it can also be reversed, and usually is reversed, so that pump comes directly after the mobile phase platform. Then we have an autosampler, and we can also have a column holder. In here, these things have been combined, and we have a detector. So here we have actually multiple detectors. Back here is a mass spectrometer that is also a detector here, and here is a UV spectrometer as well that is connected to detect also the ultraviolet visible spectra of the compounds. Now let's go through briefly also all of the different parts of this chromatographic system. So firstly, mobile phase. The exact composition of the mobile phase is something that is not pre-described. It depends on the type of chromatography. If we have reversed phase chromatography, which is mostly used, then we have primarily water, but mixed with some part of organic modifier. So these organic solvents are mostly acetonitrile or water. Sometimes tetrahydrofuran, for example, can also be used, but acetonitrile and methanol are by far the most used organic modifiers in the reverse phase chromatography. In case of normal phase chromatography, we also use less polar organic solvents such as hexane, but also some more polar mobile phase components. It's important that the mobile phase we are using has sufficiently low viscosity so that the pumps would be able to pump this mobile phase through the chromatographic system so that the pressure in the system would not go too high. So we want to have a reasonable pressure. We call it the back pressure, so the resistant pressure to the flowing of the mobile phase. And this needs to be sufficiently low so that the pumps could actually handle it and still produce reasonable flow rates. So when we are using reverse phase chromatography, or also when we are using helichromatography, for example, we use water phase. And it's very important that the mobile phase, which is a water phase, we usually call that a water phase, that it would be buffered. So sometimes people can also say, my buffer is acetic acid buffer with a pH 5. So what they mean is that they use water as one of the mobile phase components, and this has been buffered by the acetic acid buffer with a specific pH. And this is extremely important because ionizable compounds can dissociate in the mobile phase, and depending on if they are in the ionized form or in the neutral form, their retention times will be vastly different. And of course, because we use retention times to identify the compounds with the analytical standards, we want these retention times to be the same independent of the sample. So we need to keep the pH constant for the ionizable compounds to elute at the very same retention time with all of the samples. Mobile phase should also not contain any particles, and this is to avoid any clogging in the system, in the column, before column or after column. And for this, filtration of the mobile phase is very important. Usually the tubes that carry the mobile phase from the bottles to the pumps also have small filters, but additional filtering with about 0.2 micrometer pore size filters is suggested to avoid any kind of potential clogging, any particles reaching our system and damaging our HPLC instrument. Also, it's very important to degas the mobile phases, and usually this is done online. And this is important for two reasons. Firstly, when the mobile phases are not degassed, then bubbles can form in the pumps. And what happens when the bubbles form is that the pressure in the system starts fluctuating. And with the pressure also the flow rate starts fluctuating. So we can set in the computer program that we want to have a flow rate of 1 milliliter per minute, but if there is a bubble, then the system actually aims to pump 1 milliliter per minute, but the bubble, due to the bubble, the pressure, the back pressure is varying, and therefore the actual flow rate may be only maybe 0.3 milliliters per minute, or it can just change very randomly. And this results in a case where our retention times will vary a lot, and they will be mostly shifted much later, so we can't really make sense of any of our chromatography. Additionally, even if the bubbles don't form, then we can have worse peak shapes. So we might have tailing and fronting peaks, so that means that our peaks are not anymore symmetrical. And we might have some part of the peak being fronting, so we have a bit of a front in the peak. So therefore, degassing and filtering are two very important parts in the preparation of the mobile phase. This mobile phase is then pumped by the pumps, and pumps are extremely important part in the HPLC because they guarantee that the mobile phase is flowing through the system, through the column at the designated flow rate, so the flow rate that we want to use. And HPLC that we often use in an abbreviation about liquid chromatography actually means high performance liquid chromatography, meaning that the resolution in this chromatography is very high. But sometimes, and especially in the older literature, you can also see high pressure liquid chromatography, which comes from the fact that in analytical chemistry, we actually use these pumps to create this high flow rates, and in order to achieve high flow rates, we also need to have higher pressure than, for example, in usual column chromatography, where the mobile phase is almost flowing through the system based on the gravity. But here we actually want to apply high pressure to get good flow rates. And the flow rates that we are talking about depend exactly on the column length, column diameter, as well as the column particle size. But usually for HPLC, we are talking about flow rates around 1 milliliter per minute, slightly less or slightly above, depending then on the column. And we can also have an ultra high performance liquid chromatography, so UHPLC, which is now about 15 years old on the market, and it is performing even better in the sense that it is giving even higher resolution by just providing narrower peaks. And the key to that is having even smaller particle size in the columns that we are using in the chromatographic separation. However, the smaller particles also cause higher pressures that are needed for pumping the mobile phase through the column. And in case of UPLC, the pressures can be up to 1,600 bars or sometimes even above. The limitation here comes from the pumps and what is available in the pumps. Of course, also all the connections need to be pressure. They need to be able to withstand these high pressures. So this UHPLC also means that the pressures are ultra high compared to the high performance chromatography. We can have 1 or 2 pumps depending on instrumentation that we have, and we can mix mobile phases. So in case of 1 pump, we usually use mixing before the pump, and we can mix 2 to 4 different mobile phase components. In case of 2 pumps, we pump 2 components separately and we mix them after the pump. This mixing of the different mobile phase components is useful for twofold. Firstly, in case of reverse phase chromatography and helichromatography, we very often use gradient dilutions. So these are cases where we change the mobile phase composition during the elution. But it's also convenience in this sense that if we want to test different mobile phase compositions, then it's much faster to, and also more economically reasonable to try to change these ratios in the instrumentation rather than manually mixing different mobile phase compositions together. Now we carry the sample with the mobile phase that is pumped by the pumps to the columns. And columns are here always tightly packed with different stationary phase particles. We don't have any capillary columns in HPLC, and this comes simply from the fact that the resistance to mass transfer inside the mobile phase would become too large in case of liquid chromatography. Simply the mass transfer in the liquids that are used as the mobile phases are much larger than is the mass transfer in the gases that are used in the gas chromatography, where we can use capillary columns. And these particles are usually silica particles that are either then pure silica or for which the surface of the silica particles has been modified chemically so that we have different properties of the stationary phase. The particle size in the particle size in the HPLC is usually a few micrometers, and it can go down to 1-2 micrometers for UPLC columns. So it is in the micrometer scale, and the lower the particle size, the higher pressure we need to actually push the mobile phase through. The smaller particle size is, of course, beneficial because they allow more even packing of the column. So that means that the eddy diffusion impact on the theoretical plate height is getting lower and lower and lower. So that we theoretically can achieve a lower theoretical plate height and therefore more efficient chromatograms, narrower peaks. The columns in HPLC are much shorter than the GC columns. We are talking about a few centimeter range. I would say that the smallest ones are a few centimeters, 2 centimeters, and the longest are somewhere around 30 centimeters. To the current UPLC systems, The normal column lengths are somewhere from 5 centimeters to 10 centimeters, but they can be also shorter. And for example, to a UPLC system, you usually today even can't plug in a 30 centimeter column. The column holder, the column thermostat is simply not long enough. Usually the 15 centimeters is the maximum length that can be installed in the UPLC system. The HPLC column standard length is 15 centimeters. This is something that we usually start with when we are developing a new chromatographic method to determine new compounds. And the reason why UPLC columns are shorter is because in UPLC usually we already with this length of the column do achieve a reasonably good separation. And if we make the columns longer, then the separation simply does not really improve very much further, but the analysis time and the run times will increase. So usually the optimize is somewhere around 10 centimeters. Depending on the type of the chromatography and the inner diameter of the column is around a few millimeters. And one of the big problems in HPLC is the column clogging. So this means that the columns which are packed with very small particles can become clogged if our samples or our mobile phase contains any particles that can just clog the columns. So therefore, it's very important that the samples as well as the mobile phase is filtered. Usually syringe filters are used to filter the samples. And it's also important to be sure that the samples would not precipitate in the column, so that the samples are actually soluble at all mobile phase compositions that are pumped through the column. And in order to avoid any kind of unexpected clogging, usually the actual analytical column is equipped with a pre-column, which is usually very, very short. It may be just a few millimeters, and it has also much larger particles. But if there is something that could theoretically clog the analytical column, then it first actually clogs the guard column, and this guard column can be very easily replaced. So this guard column is, or pre-column is taking care of the fact that taking care of our column and is protecting it from potential clogging, or also other kinds of reactive compounds, for example, that could be somehow getting into our system from the sample. It's important that the columns are taken good care of. That means that the columns are well washed if the analysis are finished, so that no dirty samples or something like that is left into the column. If they are, they can still precipitate in the column and make your columns not usable in the next runs. So this is important. And another thing is that columns should also not dry out. So that means that if you are not using the column, then the column ends should be closed with specific caps. So otherwise, the stationary phase will get chemically damaged, especially in case of reversed phase chromatography. The column types that we use depend, of course, on which type of chromatography you are using, but there are generally 4 important interaction types that can be the heart of our chromatographic separation. A natural one is the analyte stationary phase interaction. So the more affinity the analyte has toward the stationary phase, the slower they are eluting from the chromatographic columns. Mobile phase stationary phase interaction is also very important. Mobile phase stationary phase interaction is important for the mobile phase to be able to essentially kick off the analyte from the stationary phase and make it elute further. So kind of competition between the mobile phase and the analyte for the surface of the stationary phase. In reverse phase chromatography, however, interestingly, analyte mobile phase interaction is also very important. And this is important that because analyte that has some interaction with the mobile phase is able to move through the column with the mobile phase. While mobile phase interaction is also important in reverse phase chromatography, and this is something that can additionally push the analyte molecules to the stationary phase if the analyte mobile phase interactions are not as strong as are the mobile phase molecules interactions. And we will look these further in the specific parts of the chromatography types. Lastly, when the compounds have been separated in the column based on the specific interactions, we also need to detect the chromatogram. And this is done by the detectors. The most traditional detector in liquid chromatography is the ultraviolet visible spectroscopy detector. It can be a one wavelength detector or a detector where we can choose one wavelength to detect the compounds. It can also be a full spectrum detector, which then is based on the diode array device, which allows to detect the full spectrum. So we can get also somewhat qualitative information as much as the low selectivity of the UV spectroscopy allows. And ultraviolet visible spectroscopy is very useful because it allows detecting all kinds of compounds that have some kind of aromaticity. So at the days when mass spectrometry was not very common yet, or not common at all, UV spectroscopy was the working horse of the HPLC. And because all analytes actually don't absorb at reasonable wavelengths. So this means that maybe they don't absorb very much above 200 nanometers or 250 nanometers. Very often derivatization was used also in HPLC, or maybe not very often, but fairly often. So for example, one good example are amino acids that have been determined essentially since the first days of the modern HPLC apparatus, but because they don't absorb very well in UV vis, they were first derivatized and then separated with the HPLC, and thereafter UV visible spectroscopy could be used to actually also detect and quantify these compounds. Another good detector is fluorescence detector, especially if we have compounds which are fluorescent, or sometimes we have compounds which can be very selectively made to fluorescence, again by derivatization. This is also something that has been used, for example, for amino acid or amine determination in general. Today, mass spectrometry is increasingly used. And this is very good because a mass spectrometry does have an advantage in the sense of selectivity. So we do receive not only the retention time, but we also always register the mass to charge ratio of the compounds and also fragmentation information. So this means information about the different functional groups that are present in the compound. So this means that mass spectrometry can give us additional selectivity. So mass spectrometry definitely is applied more and more. However, there are still very many applications where the research question or the analysis question is so well defined that there isn't actually any need for mass spectrometry. This is especially, for example, in synthesis purity detection. Actually, in this cases, UV spectroscopy usually performs even better than the mass spectrometry can. Or the same in determining the assay in the pharmaceutical products. Or again, UV spectroscopy detector in HPLC can be used for these tasks very, very efficiently. For compounds which are oxidizing or reducing, electrochemical detector can be used. It's not as widely used as neither UV spectroscopy nor fluorescence nor mass spec. And for ion chromatography, conductometric detector is a natural choice because we are separating ions which produce changes in the conductivity of the mobile phase. However, also for ion chromatography, we can use mass spectrometry for detecting the ions. So this was shortly about the instrumentation that is used in HPLC. And next we are going to look into the different types of chromatography in HPLC.